All right, guys. I'm going to go ahead and get started. So, again, as I sort of said last week, this class, we're just going to sort of do a refresher on what we've learned to date. Hopefully that'll give you guys a little bit of time to catch up on reactions that we've learned, and also perhaps to go back and look at some of the work in terms of Organic Chemistry 1, if you haven't had a chance to really do a lot of that. Again, I think one of the best practices to sort of get you guys making sure that you remember all the reactions and learning all the reactions is to sort of do synthesis problems. And historically, what we'll often see is a problem, at least it's sort of ones that take us a lot of time to do, or ones where we'll say start with a molecule like this and say, can we make this from methanol? And so sometimes, especially on like work problems, for example, where you have a lot of time, an infinite amount of time, will often give you this problem, and literally every single methyl group in this molecule would have to come from methanol, and certainly you can do that. But I thought that what I would do today, instead of going through that problem, because that might take us a whole half hour to do, we'd look at it at a little bit of a different light in terms of something that might be interesting to sort of think about. So, you guys have learned a little bit about, obviously you guys know there's different isotopes, different molecules and stuff like that. And one of the things that I think is really neat, one area of research, a good friend of mine is actually doing work in John Vidaris' group at Alberto. One of the things that they'll often do is they're trying to study and understand biological systems and how different molecules are made and things like that. And one of the tools that they'll often use is sort of isotopic labeling. So, for example, if you're curious how some molecule might be synthesized in a biological setting, what you may do is you might synthesize a proposed intermediate in that pathway, label it with an isotope, and then see if the natural product comes out, has that isotopically labeled compound within it. And so I thought from a standpoint of going over some synthesis problems to sort of practice what we've learned to date, we could sort of start thinking about this in a way that might put a little bit of a twist on some of the synthesis problems that we've done. Now again, we could imagine doing this molecule and imagining doing this problem in terms of making it every single molecule from sort of methane, or sorry, excuse me, from methanol. But another way that we can imagine doing this is to say, all right, what if we wanted to isotopically label this molecule? And specifically, what if, say for example, we were doing some type of experiment where we want to isotopically label the specific position on this group, right? And then go ahead and take that and see where that group might come out. So I thought this would be a nice little twist on synthesis problems. So what we're going to do is, not only are we going to try to synthesize this molecule for methanol, but one of the things we could think about is, if we were to try to make this molecule and have C13 within this, how would we do that? So I thought we would start by sort of thinking about how we might make this ketone, but then make it specifically with a single C13 methyl group in it, right? So methanol, you might imagine, is fairly probably an expensive stockpile. Certainly you can buy C13 labeled methanol, so that might be an actual starting material that you might use in an experiment like this. Okay? And so when we just look at this methyl group on this side, the experiment might be fairly easy, right? So how might you guys imagine sort of making this from methanol, right? We want to do a retrosynthetic analysis, right? And so in terms of breaking this bond, right, that's going to be the easiest thing that we can do, right? Because then we've isolated that methyl group, and then simply all that's going to happen is we're going to sort of go back and start doing some functional group modifications and so forth. So how might we make this disconnection from a retrosynthetic standpoint? What might be our sort of ketone part of the molecule, and what might be our methyl group part of the molecule? There's multiple different ways, as we've seen, but let's have an example. So we can do a Gilman, right? And so one thing that we could imagine is having a Gilman reagent. It would be C13 labeled, right? Okay, and then the other component of the molecule would be what? What would be the partner in the Gilman? Acid chloride, right? Right, so you would have this, and you would have the acid chloride, right? And that's going to simplify the molecule fairly dramatically. Again, we don't have to worry about this chloride. It turns out that this acid chloride is commercially available. It's very cheap. I think we may even have some of this in our lab. And now this question simply becomes, how do we make that Gilman reagent from methanol? And this is something that I hope that all you guys would be able to do by this point, right? So there's two there. Okay, so what do we make the Gilman reagent from? Yeah. Okay, you're skipping a step. So how do we make the Gilman? What's the, yeah? Well, let's just work backwards. So from the methyl lithium, right? We're going to make that from the alkyl lithium, right? And then how are we going to make that alkyl lithium? Yes? Yeah, it's some sort of, right, so usually it's copper iodide, right? And so what you end up is the Q-Li, right? And now from this alkyl lithium, now you're going to make that. Exactly. Right, and then right, and so exactly, so PBr3, this will be lithium, or you can do lithium halogen exchange, usually just lithium, 2Li. So this is a fairly, sort of simplifies the problem fairly easily. So this would be a fairly easy, I would hope, synthesis problem to sort of carry out. But if we start to take it to other areas within that group, right, we might get into, this might become a little bit more of a difficult synthesis problem. So what I like to do is start to think about how we might now make this at the ketone. Okay, so this we're going to come from this group. Well, we've sort of simplified it less. We've sort of simplified it fairly quickly. We can at least go to the acid chloride if we want, right? So we can just sort of do what we did here, right? Right, this is our C13 plus the Gilman. Right? How do we make acid chlorides? Right. So we're going to make it from the carboxylic acid, right? And what's the reagent? All right, so this would be SOCl2. Okay, and now we're at the carboxylic acid, and at this point I think there's a few different ways that we can go about synthesizing this, and I kind of wanted to hear what you guys would think, and again, at this point, you know, I think certainly from the acid chloride standpoint, everybody would probably do something similar to this, but at this point I think there's going to be a lot of variability that's going to really be dependent upon sort of what your sort of go-to type of reactions are, and this is why sometimes it's worth it at this type of step. So really, I know I talked to somebody in my office was saying, I really don't like doing retrosynthesis arrows. I'm uncomfortable with them. Well, this is where it becomes sort of essential, right? Because there might be a few different ways that we can go about making this molecule, and it's worth it to just think backwards a couple steps. And if you just stick with one and go with it, it might be a nightmare. But if you think about, just spend the time to think about a couple different ways to move backwards, you might find one of them may just be easier to do, right? So what would be some retrons, if you will, that we could do here, yeah. So you could do a Grignard and CO2, right? And so in this case, what we would end up with right, is CO2 gas, right? And this would be our 13 labeled CO2 gas. That's okay in terms of paper chemistry, but the question is, how do we make CO2 gas from methanol? I think that's where it becomes a little bit tricky, right? Like, how would you guys think that you might make CO2 gas? Yeah. Right? Yeah. Well, no, but specifically CO2. So if we wanted to take methanol and make CO2 gas from it, how would we do that? Right? I mean, that's what you might think. Or we can combust it, right? No, so it's not a bad idea, Margot. Yeah, just stick it in an engine and stick your flask out to your exhaust pipe. No, but I think, right, I don't know that we've learned this, right? I think that you could imagine a scenario where you might take Jones reagent and oxidize. You'd go to the formic acid, and then maybe it might oxidize to carbon dioxide. I actually don't know if it would do that or not. Add to that, even though we don't really worry about it too much in terms of paper chemistry, the fact that handling and working with a gas as a sort of reagent might be tricky. But yeah, I mean, if you guys did that and you went to CO2 and you said Jones reagent, I probably wouldn't argue with you on an exam because you are sort of going to the highest oxidation. I never told you that you couldn't. But it might be a little bit tricky. So this is fine, at least on paper. I don't know if it would actually work, but yeah, you could maybe imagine that Jones might allow you to get here from the methanol. But what if I told you that wouldn't work? We probably don't want to go through the CO2 intermediate. What's another way that we might imagine coming from here? Say that again? Okay, so Margot's thinking that we're going to go and break this bond here, and you've sort of thought ahead in a two-step process, right? So what Margot's thinking is, I'm going to use, so we've learned about carbon dioxide being certainly an electrophile, as was sort of just seen with CO2, but what Margot's saying is we've seen it come in nucleophilic form, and that could be cyanide. Hold on one second. So we just want to go through Margot's idea. So in fact, in Margot's idea, we wouldn't start with that bond, right? There would be an intermediate, and that intermediate would be what? The cyano, right? Right, so Margot's thinking, let's try the cyano. I hadn't actually thought of this one, so let's see where we can take it. And her thought is that once I have that cyano, again, because it's just hydrolysis of that cyano, then we're going to be at some halogen, bromide. Just for completeness, we'll just say bromide. And what Margot wants to do is potassium cyanide. So Margot's got a death wish. Some organic, right? So potassium cyanide. Okay, and now this isn't where our carbon is coming from, right? It's this one right here, right? So we've got potassium cyanide. And now the question becomes, how do we make potassium cyanide from methanol? What's that? Yeah, it would be, it's kind of up the same angle as I think what we dealt with. Okay? The ketone or the aldehyde? Hold on. We're going to go through this route first. Right, so the point is, I think this was good. This is where retrosynthetic analysis is important, right? Where it's like, okay, well, this would be one way that I can make that. I know that. Let's just get it down there and write it down and see. Might there be a way? I think this is where the CO2 type, same situation with CO2 comes up. It's like, okay, I've seen that as CO2. Cyanide, I know is a good nucleophile. I know that it's there. But then the question becomes, okay, now I just got to convert methanol to cyanide. And as I said, we can imagine a scenario where maybe you have, say, the amide, right? And somehow the formamide, I guess it would be, and then we would basically take the formamide and just try to eliminate the heck out of it, right? And formally, that's how the relationship is between the two oxidation states. But again, we really haven't learned that chemistry. That's the type of thing where if you sort of showed it on a synthesis problem and started showing elimination, I would give you points for creativity, at least thinking to that extent, but it would probably might not work. And so we may want to say, well, what do we know could work. And so maybe we don't want to go the cyanide route. You had another... Okay, so if instead we're going from the ester, certainly we know that esters can be sort of retrons to carboxylic acids, right? We can simply hydrolyze these with acid and water. But does this help us at all? Maybe. Maybe. I mean, what can we do now that we're at the ester? Well, then we're just going in circles, right?
What if we don't read into that, the active molecule?
Okay, so everybody's paused with the ester and isn't quite sure. And I think that, again, sort of says, okay, well, we can do that, but then now we're still stuck, right? That might be useful for a different type of synthesis, but maybe for this one, not that great. But let's just try, because we really haven't changed oxidation state here.
Why don't you go read into that?
I think that's a good idea. Let's try that.
Leave an alcohol in, primary alcohol.
Right, so now we've got the primary alcohol, it's going to be Jones. Right, we all know that alcohols can be oxidized up to the carboxylic acid with Jones. This is simply thinking backwards from that functional group, right? And now we... Okay. Okay. Wait, hold on. I'm trying to think what you're saying. So you want to do...
I want an alkaline attacking the positive.
Oh. Wait, so you don't need to protect it then.
Well, because when you look at ammonia, you might get rid of the alcohol.
No, right. So you would generate an alkoxide, right? So that's pretty standard. So you want to basically take the epoxide.
I want an alkaline attacking the epoxide.
So okay, let's talk about that for a second. So if the alkyne attacks the epoxide,
Well, it would be
there would be an intermediate.
No, the carbon coming off of it. It would be
1, 2, 3, 4.
I'll say it.
Right. So what you're sort of getting to is this.
Yeah.
And then you would reduce that, right? But what might be the problem here? Well, not only how are we going to make it, how are you going to, you got to label this C13, right? And so if we choose this one, how are we going to control that, right? So that's a good start. And then we have to break it down to the epoxide, and maybe we can do it. But there starts to become problems. Specifically, the epoxide might not be the easiest thing, because then we got to go back, and we've probably seen problems where we've made epoxides for methanol and so forth. But again, I think the bigger issue here is you're selectively trying to get that there. It might not be the best thing. But no, that's at least thinking. Again, just to sort of complete this thought, how would we reduce that alkyne down to the alkane? What would liquid ammonia do? Sodium and ammonia. Is that what you're talking about? So what would sodium and ammonia do? Right. I mean, there's no cis or trans here, but it would go to the alkene.
I wouldn't go all the way.
No. Remember the guys, just quick refresher on alkyne chemistry, right? Do you want to go to the cis, alkene? Oh, that's... Hold on. Let me just refresh here, because that's kind of the point of this class, is refreshing. So let's refresh. Okay? All right, so Lindlar's and hydrogen gets you to the cis alkene, right? We just said, how do you get to the trans alkene? Sodium and ammonia. So remember, liquid ammonia is not really going to do anything. It's the fact that you've got the sodium in there. It's, in fact, the electrons in that sodium that's doing this. Right? That will give you trans. And then what is Lindlar's? Poison. Why do we need poison palladium? Right, and what would happen if it's not poisoned? Right, so exactly. So we just use some standard palladium catalyst that's not poisoned, will likely reduce it all the way. That's just a refresher on the fact that we have this versatility within alkynes, that we can get this stereo control or we can reduce it all the way, but it's certainly worth mentioning. But yeah, I mean, this is good. It's good you're thinking about the epoxide.
Do you need a technical file when you use that or not?
No, not at all. Because, I mean, when would you protect it?
Right before you reduce it.
Oh, so you want to protect it here.
Yeah. Like when the alcohol go away.
No, probably not. I mean, I've seen actually it happening in actual life. Like a friend of mine was trying to reduce an alkene and he kept reducing off his alcohol. But, I mean, that's part of the thing, right, guys? I mean, this is sophomore organic chemistry or whatever you want to call it, sort of second, whatever. Not sophomore, a lot of you guys are juniors and seniors. But the point is we're just in that sort of introduction to organic chemistry. And so when we say palladium and hydrogen, there's a million different metals that could do this. So if you want to protect it to be safe, that's fine. Under certain conditions, it might sort of get rid of it, but I don't even think that's something your book really describes at all. So you wouldn't need to, but if you did, it would just sort of be overkill, but it's not. But again, I mean, this is, thinking about it, again, this is a retron. This is why we do a retron. We have an idea of how we would make that. We just work backwards, evaluate it. Is this going to be helpful? So this is a good route, but I'm not sure. I think it's going to have a few issues. So just give me a second. Let me just create board space because I'm out with it. All right, so we've gone through a few different retrons. Nothing's really shown a clear picture of what might be the best way to make it yet. Wait, we had the Jones reagent at one point, right? Okay, so we have the Jones reagent. How else can we, what other, yeah, you got your hand up.
No, when you from there, you have double bond and double bond.
So let me ask you a question. Why are you guys keeping wanting to have these double bonds?
Because you hit it with the double bond created something you like.
Do you want to do like Wittig type chemistry?
Yeah.
So that's fine, but I think you guys are missing something that should jump out at you anytime you see an alcohol. Right? This is chemistry that you guys have actually done physically in your Organic 1 lab class. Yeah. Well, that's what effectively happened in your lab, but when you have an alcohol, right, that's where I thought we were going before, right? If we just want to break that bond, what would be the retron to that? Well, right, exactly, an aldehyde, that's technically formaldehyde, right? Right, and so it would be that aldehyde, and what would we add into that format? That's this formaldehyde. What would we add into formaldehyde? Yeah, Grignard. Okay. Okay, so this is where I may become a little bit of a hypocrite, right? Because I just said previously that CO2 might be difficult. Formaldehyde, it sits a little bit easier with me. It usually exists as a polymeric form, so it's not like the gas of CO2. That's not something you guys would necessarily know. Formaldehyde in itself is a gas. But again, I think this is a much, at least, how would you do this reaction, at least propose generating formaldehyde now from methanol? Yeah, and I think, again, how convenient, how well that would work, I'm not quite sure, but I think at least in terms of, in this course, I think it's a little bit more fair of a proposed method to make it, right? And part of that is, unlike with this case of CO2, where you're sort of forcing it to get to an oxidation state that it's never gone before, PCC, this is basically what you're doing. You're just oxidizing it up one, right? And the idea with PCC, right, is that you're keeping water out of the reaction so that once you do that sort of first oxidation, it can no longer oxidize. And so I think this is perhaps the best way to do it, right? And you can sort of see really quickly. You might not notice it at the carboxylic acid step, and you might go through all these other things that we learned, right? CO2, cyanide, those might be the go-to ones because that's what we've seen. But then if you just take one step further back and you go to the alcohol, I think then it starts to become a little bit easier to see. What's PCC? Tell them what PCC is. PCC is pyridyl chlorochromate. That's the aldehyde, right? That generally takes compounds to aldehydes, right? This is formaldehyde, but it basically just takes it up one oxidation. So go and refresh PCC. Okay, so again, here's an example of a sort of synthesis problem that uses this. Okay, I'm going to do one more. Actually, we'll do a couple more with this because I think synthesis, again, if you sort of notice the things that I like to emphasize in the course are synthesis and mechanisms. Yes? Yes? Well, why would the Grignard not attack this twice? Why do Grignards attack esters twice? Right, because there's a leaving group. In this case, if you're attacking aldehyde, right, what's the leaving group here? A proton, right? Proton's not really a leaving group, right? So, yeah, or I guess it would be hydride, technically, right? Yeah, but no. So the reason that esters add in twice is because the alkoxide kicks out, right? So hydride, you're generally not going to have. I don't know that I've ever seen hydride in my life as a leaving group. Sometimes hydrogen at really high temperatures, but yeah, not necessarily hydride. Yeah. So right. So this would be, you mix these two together, and then step 2 would be the workup. Again, it's always sort of, I think it's one of the things that can be tricky. Yeah, it's always assumed that there's a workup at the end. They were going through some of your guys' quizzes, and there were certain steps where it was like, okay, well, is it assumed that there's this workup, or is there not? And if we sort of have it open-ended, then just pick one and go with it. So we always sort of assume there's a workup, but if you guys don't see the workup and assume that there's not a workup and show the product that would result from not a workup, that's fine as well. But yeah, usually, because that's just a slip of our mind sometimes, we don't think about the workup too much. But yeah, there's always a workup. All right, so let's do just one more, and then we'll try a few other things, but we'll just go through one more that will hopefully teach us a little bit more and get us thinking about different ways to connect the molecule. All right, what if now our C13 was in a different place on this? Let's try, let's go here, and then you guys can keep going down the road at home and keep trying this at home on your own. But let's just go through this one more together. Again, each of these synthesis problems are all effectively the same thing. They end up being very, very different synthesis problems because of the goal that you're trying to get out of this. Okay? Let me give you guys a little bit of time to think about this. And so what I'm going to do is, what we'll do this time is I'm going to want you guys to each think of right now 3 different retrons. And we'll put them up on the board, and what we'll do is we will sort of collectively decide which one we like best. Okay, so let me give you guys a few minutes to think of a few retrons. Yep. We're just going to stick with the same starting material. So we want to somehow get methanol at that position. I think this is going to be a little bit tougher one. But again, oftentimes the thing that makes the synthesis problem difficult is whether or not you can sort of see it at a certain extent. And so sometimes it just takes looking at the problem a little bit differently. That's often what chemistry is, right? It's taking a problem and figuring out the right way to sort of look at it. Yeah. Is there a way to extract a proton from propanone? Wait, so from propanone, you mean acetone?
If I had regular propane with like ketone.
Yes, this is acetone.
Yeah.
So your question.
Anyway, if I take a proton, DR2, right?
Wait, hold on.
Can I do that?
Well, Margo's asking us, can you do this? Yeah, that's the foundation of everything we've done, right? Making the enolate.
If I want to, then I want to add methanol. See, I chose acetone because the two either side,
Mm-hmm.
and then. What I was always thinking of that.
Well, yeah, hold on. Let's go through this. Let's go through the retron again. Let's just think about this from the retron standpoint. We have to work backwards. I want to sort of stick with this retron. I want to not rock the boat here. So if I want to hear 3 different retrons, okay, ways that we can make this ketone, things that can come from this ketone. Yes. Okay, so one option would be to go from the secondary alcohol. Okay, we're just gonna. Okay, we're not gonna go any backwards at that point from here. We'll worry about that later. Anybody have another one? Yeah. So C13 labeled Gilman here. Okay. Anyway, yeah, that's probably poorly drawn, but yeah, so that would be one option. Yeah. Linear with a 3-carbon chain. Well, that would get you here. So that's just a retron from that alcohol. So I'm asking from the ketone itself. So we've effectively done oxidation change. We've done this connection here. There's maybe a couple additional retrons that we could think of. Yeah? I like that, actually. Everybody hear that? Triple bond. One I hadn't thought of. That's a good idea. That's me. That would be the best idea. So that would be another. Oh, sorry. That's 2 steps back. Sorry. I just did what you had done. So we're just saying. Right? So you guys remember you can take alkynes to ketones. How do you take an alkyne to a ketone? Yeah, just like acidic water, right? So if you guys remember that one of the very first reactions we learned on alkenes, right, was to take an alkene and treat it with acid and water, and you made the alcohol, and it went to the more substituted side, right? So if you do that from the alkyne, you're going to get to the enol, right, and then it's going to tautomerize down. So I like that a lot. So, okay. Yes? So that's yeah, it's one of the same. So oxymercuration reduction chemistry. Yeah, I mean that's the same type of reaction, same idea. Different conditions, but yeah, it would lead to the same thing. Okay, so unless anybody has another one that they really want me to put down, we can sort of evaluate these. Okay? All right, so let's take a look at these sort of 3 right off the bat and start to sort of ask ourselves how we might start making these molecules, right? And just sort of think backwards a little bit, right? And so in the case of this Gilman reagent, right, we sort of generally know how Gilmans are made by this point, right? So we know that we're going to have to come from You know, in the case of a Gilman, we can think a couple steps back at this point, right? So what do we make Gilmans from? The bromide, ultimately, right? So even without having to go through all the nitty-gritty details like we did previously, if you have the bromide, you should all know you can take that to the Gilman by treating it with lithium and then treating it to copper iodide or copper bromide, right? And so what we would formally have here is bromide, C13 labeled bromide. Okay, so we know that we could probably break that one down to the bromide. Let's just think about this one. What about the alkyne? Yeah? Right, so it formally gets you the same thing. Right, so it formally gets you back to the same intermediate as the Gilman. Right, so it's going to be the same intermediate, but which one do you guys like better? You guys like the alkyne better or you like the Gilman better? Why do you guys like the Gilman better? Because it's got a name with it? Yeah, I mean, just critically evaluate it, right? I mean, what are the differences here? It took you a lot more steps to get from here to here, right? The bromide is, you know, you don't have to do anything here. You've already got the bromide, right? The other thing is you're often throwing away an equivalent, and it's isotopically labeled methanol. It's probably pretty expensive, right? So you probably wouldn't want to just throw away your material. So yeah, I would probably say this is, of these two, this is the superior one, I would think. And we've got something that's a little bit sort of simpler. You know, we're going to have to sort of break that down. I think we can, but we can at least sort of evaluate the different routes. So let's go ahead and just for board space, let's get rid of this one here. It goes through the same thing. Okay. Now, what about this alcohol? This comes back to sort of what we were just talking about earlier, right? And the alcohols, again, you should see the alcohol, and when you're looking at alcohols from a Rectron standpoint, you know, there's a couple different things that you can look at that, right, in terms of disconnections. One of them being what? Right, one of them being the aldehyde, right? So one option here would be the aldehyde. And again, anytime you're doing a Rectron like this, as you might imagine, you probably want to dissect it here, right? Because you want to go into bigger pieces. You don't want to have to carry this carbon around, have to worry about it later. Right, we do this aldehyde. Right? Now, how would we make that Grignard? From the bromine, right? We're going to make that from the bromine anyway, right? So, again, for the same reasons, this probably would be no better than this, getting to the same compound. The only thing you may want to consider is, yeah, I don't know. I don't know. Do you guys think of anything else at this step that might be perhaps useful? Yeah, I really can't think of it. Maybe an epoxide, right? But even the epoxide, the issue is with this is you've got this carbon right in the middle. So you could imagine perhaps doing it from, which may be a little bit different. Maybe you could imagine it coming from like this epoxide. Right? This wouldn't have the same selectivity issue as the other one did, right? Why? Right, because a good, better nucleophile will go after the less substituted side, so it's going to attack this side, right? Right, and so at this point now we're at an epoxide. How do we make epoxides? Right, MCPDA. Right? And now we're at two intermediates that are kind of like, I don't know, I mean, these two, now we've got something to sort of work with to a certain extent, right? I feel like some of you guys might look at this and might see it as something that, you know, that you've got a real quick idea of how to make. Some of you might look at the bromide and have a better feel for it. But again, we can sort of take both of them back and start thinking about it, right? So in the case of the bromide, how do we make the bromide? Do you want to do radical chemistry?
Well, the round is
Right,
so that's
right. But
but
what's the standard way? What's the first way that you guys? Well, you can make it from double bond. I wasn't thinking that. Right, that gets us right back to here, though. Right, it's not clear that that would be. So how would you, again, how do you add HBr anti-Markovnikov? Peroxide and HBr, right? Right, so you could do this. Okay, but again, it's just the same place that we were before, so it's really not anything that's too. But what's the other way that we make bromides? PBr3, right? From an alcohol. Okay. And now from that alcohol, now we effectively at something that we were almost at before, right? How do you guys think we would make this from methanol now? Formaldehyde, right? So exactly, everybody hopefully sees that, right? This would effectively come from formaldehyde, right? And ethyl Grignard. And then as we talked about before, this would probably come from PCC. Okay, so yeah, so that's not a bad synthesis. Now you might imagine some different ways for the alkene, right? Certainly one way that you do it is to make the alkene bromide and then, you know, and then go this route, right? But there may be other ways that we could perhaps do this, one of which somebody was bringing up before. What do you think? Okay, the alcohol, you can, so you want to go to here. Sure, so we could take that, right, so if we did, well, wait. Right, so you're going back here. Okay, so yeah, so that's one way that you could go this route. What's another way that might just use different chemistry? Yeah. Accumulate and do SN2 reaction. Well, we're enolate.
Right, so I would put that acetone related to protein, the oxidable bond.
Oh, I see what you're saying. Okay.
And then go backside attack on the carbon 13 that has a bromine attack and the rest of the carbon.
Okay, well, let's think about this for a second. So if you have this enolate, I'm just trying to understand what, yeah, hold on. So say it again?
My carbon 13 has all the carbons attached. And I was saying how I chose acetone because I decided to put it in.
Yeah, but that would be an issue. That would be more of a problem than anything, right? That's because then we have, even if we did go through this route, right, we'd get scrambling. No, I mean, the reason why I want to continue in this route is I think there's one quick way that we could do it from this alkene. That's perhaps a reaction. I mean, what's one of the ways that we know double bonds? Yeah. Say it again? You're thinking forward. Right, you're thinking about taking this and making methanol.
Oh, we're not.
No, we're doing a retro. So this is retrosynthetic. So you're going forward. So that's right. So ozone on an alkene would go to the carbonyl, and then we could take that to methanol. But we want it to start from methanol. So that's why we're doing retrosynthesis. So that's how you break an alkene. How do we know to make a double bond that's an alkene? Wittig, exactly. Right? And so if we had carbonyl, right? We can start from this Wittig salt, right? How do you make Wittig salts? right? Or in this case, I have the bromide, so it would simply be right? To make the Vidig salt, all you do is take triphenylphosphine, treat it with the alkyl halogen. So yeah, it can be an iodide, in which case you can have the iodide salt, right? And then this is just what? PBr. PBr3. Okay, so again, I don't want to bore you guys to death with synthesis here, but we've sort of used this as an opportunity, I think, to go through some of the chemistry. And what I would tell you guys is, you could certainly go home now and just move that C13 up here and try to come up with that problem. You can move the C13 down here, try to do the next problem. The C13 over here should be really easy if you're looking at it the right way. So there should be a couple steps. It might only take you guys a couple steps if you go through this C13 here. So I'll let you guys try to figure that one out on your own. Okay, so we have about a half hour left. I have some more stuff written down, which we can do. But what I generally like to do in my review type sessions is sort of open up the floor to some questions about specific things that you guys might want me to go over. Yeah, so Ray? Ray, yeah, what's up? Guys, quiet. Yeah, so I was just having this discussion, because I think you guys wrote this. I'm sure you can. Under strong enough hydrogen atmosphere and with the right catalysts, I'm sure there are methods. In fact, I know there are methods. I can't name those methods off the top of my head, but I know that you can do it. Whether Rainy Nickel, for example, would do it. Yeah, probably if you were in like a bomb and had 100 psi or something. So, yes, I think it's more important that you show that it is a reduction. If you've done something like that, that it is a reduction. But the go-to should generally be lithium aluminum hydride or maybe borane. But yeah, that under harshly and strong enough conditions, probably, definitely. But we haven't really learned that. Yes.
You want us to be very selective about synthesis?
Okay, so the question is, in a synthesis problem, do I want it to be selective? Yeah, I want you guys to have the best synthesis problem that you can possibly give me. So in the heat of the moment of an exam, right, you're not going to have all the time in the world to think of the best method. If you're doing a practice problem on your off time, I think it's worth it if you go through synthesis and you're like, oh, I got there, but I feel like there should be a better way. Great, that's even better. There's lots of different ways to do synthesis problems, and that's one of the best things about them. In the heat of a moment in an exam, you're better off getting there than not. But to make sure that I'm never going to say, do this in 4 steps or less, or do this in 3 steps or less. You guys have as much time as you want and as many steps as you want to get from point A to point whatever. However, selectivity issues are, I think, a little bit different. I mean, I put selectivity in terms of that in the same vein as I would put like diastereoselectivity, selectivity, right? So if you're trying to if I give you a problem and it's asking you to make a diol, and I've shown the diols with certain stereochemistry, I'm expecting you guys to think about stereochemistry. Does it mean that if you draw the wrong diastereomer that you're going to get it all wrong? No, but I'll want to reward the people that got it right, so you will lose a little bit. And I would say the same goes to any selectivity. And that same goes, we've sort of seen an instance here where there's 2 possible enolates. How would you get a transdiol? Depends on how you define transdiol. Right? And meanwhile, if you come from the trans, right, then it's going to lead to the opposite. And you guys can sort of figure this out on your own, but you can see that right? It's going to depend upon the alkene that you start with, right? So depending upon the alkene that you start with, you will get a product dependent upon it. So this is just oxidation from the top base, right? So yeah, so in instances like this, you know, and if I show a diastereomer, I am looking for the chemistry that would lead to that one. If you happen to not, if you get to the opposite, you will certainly get more points than the person that wasn't able to make the molecule at all, but you're not going to get as many points as the person that gets the right stereochemistry. How close you are is going to depend upon the difficulty level of the problem and the mood that we're in. So, yeah.
Will you do all that after the like, can you play with it? I'm trying to do it.
Palladium for what?
No, please.
Oh, Claisen?
Yeah.
No, we're not going to, we haven't even talked about Claisen yet.
Okay.
Oh, Claisen, Claisen condensation. I was thinking the pericyclic reaction Claisen. Yeah, no, the Claisen condensation, you could certainly imagine doing. I mean, it would come from,
You're there.
yeah, you'd probably come from the ketone. This would go kind of like where maybe Margot was going, right?
What I got from there was,
Hold on. So what you're sort of saying in a Claisen, if you want to do a Claisen, what you're sort of talking about is and again, this is, I think, kind of what Margot was referring to. The issue here would then become selectivity, right? Because what would happen is you'd have to react these two together, and then furthermore, actually, I take that back, because then you'd have the ketone there as well. So you'd have the 1,3-diketone. You'd have to somehow reduce one of those ketones over the other. And I think that's where you're going to end up running into the problem. Now, I think what Margot might be saying is if you did this, if you did that, then the intermediate that you would have, and maybe this is what, is this where you're sort of talking about?
But if you did an elbow, it would have been constantly
Hold on. There you go. So,
It doesn't matter what we do.
right, and then so I guess that's fine. Yeah, so you could imagine protecting one as the acetal, reducing the other, then deprotecting. Yeah, that's fine. I mean, you still get back to that same problem that we discussed earlier, though, which is that now you're going to get a mixture of the C13 at both places because you're inherently coming from the enolate that could be at either. Because when you have, how are you going to make this enolate over that enolate? And depending upon which enolate you make, then you're going to sort of run into this issue. Right? Because how are you going to, because they're going to come from acetone, but then you got to deprotonate one side over the other. And I think that's where you'd run into the problem. So again, if you get there that route, that's better than not getting there. But this is one of those scenarios where you can see if you can make it from the acetone. In practice, that's one of the great things about synthesis is you're never really wasting your time. Practicing is always good, even if it doesn't feel like you're making headway, you are. And so you can certainly take it back and you can say, okay, well, then there was this problem with it. Let me see if I can come up with a different way. And so that's the nice thing about synthesis is you can spend a lot of time on a single problem. Okay, any other specific questions? Yeah.
We have a long chain with carbonyl and double bonds on it, and we use lithium or we use hydride. Would it reduce everything, or what would it
the question is again a selectivity question. So you're saying if you had a long chain molecule with double bonds, carbonyls, and what else did you say? Carboxylic acid. And you're going to take this and treat this with lithium aluminum hydride. Yeah, I mean, what would happen if you took this molecule and treated it with LEH? Yeah, you'd reduce everything. You reduce everything. So this would be an alcohol, this would be an alcohol, this would be an alcohol. You get probably every permeation of diastereomers you can imagine. The alkene would be, well, yes, for your sake, yes. The alkene would be fine. It's fine. The alkene's fine. I'm not gonna, we'll leave it at that. The alkene's fine. Yes?
What's the alkene? I see the alkene as a bond with negative. And
Yes, you're right.
LH is
We're going to leave it as alkene won't reduce. It might, in truth. There's actually hydride, there's something called superhydride.
Yeah.
It's a borate hydride that you can use. So yes, these types of hydride, and there's actually ones that are fine-tuned to do the 1,4 reduction. So yes, you can imagine adding 1,4 hydride. You guys don't have to worry about that. But yes, your intuition is good. All right, so yes, so any other questions? Is that a hand up or just stretching? Just stretching. Okay, all right, so I'm going to show you guys one more thing then, and then I'll let you guys get out of here. So we talked a bit about, again, keep practicing synthesis, keep going over mechanisms. But I do want to just show you one more reaction that's sort of related to what we've seen here that I think is an important one and sort of worth showing, and then I'll give an example of where this is sort of used. So I was actually really frustrated as I was looking through my notes and noticed that the book didn't cover this. But, we've seen instances where ketones, right, in the presence of, say, an amine, right? We've seen instances where we can take these sort of secondary amines, and what we can do is we can generate the aminium, right? And then what can happen is that aminium will tautomerize, and we'll end up with the enamine, right? And this can be a nucleophile, right? And so nucleophilic. So that can be the nucleophilic encapsulation. But within this intermediate is, I think, something that's just glaring. It should be glaring to you guys, right? The aminium. What kind of reactivity do you guys think that aminium chemistry has? Very reactive. There you go. If it doesn't tautomerize to the enol, right, the aminium would be very reactive. But how? In what way? It's a really good electrophile, right? So if you have a nucleophile, you can imagine getting to systems where you can start to build amines. And then I said, okay, well maybe we discuss it in the amine chapter. Come back to the amine chapter. And then I went to the amine chapter, and the amine chapter didn't discuss it either. So I said, okay, they need to know this. Okay? Because in terms of making amines, there's nothing different here, right, than what we've seen previously, right? Carbonyls, we can make enolates. Carbonyls, we can add to them as nucleophiles, right? And so then you go ahead and spend this time learning that when you condense a carbonyl with a secondary amine, you generate these enamines to make them better nucleophiles. And then what you don't discuss, or the book doesn't discuss then, is the fact that you take them, and there's that intermediate, you can also make it a good electrophile, right? And so I'm just going to show you guys one reaction. Again, this is the type of question that I'll put up here that would be the sort of standard mechanism type question that I'll often give one of on an exam, which is a reaction that sort of includes everything that you've seen, but might just be slightly different. And so, figure what we can do is we can go through this reaction, okay? So if you have okay, and you have, say, for example, okay, if you take this aldehyde, this ketone, and say, for example, ammonia, and you mix them together, a reaction will take place that's called a monic reaction. I'm just out of board space over here. And what this reaction is formally an aldol reaction with an aminium. So if you take an amine, you react it with a ketone and say, for example, an aldehyde. What you will end up with is what we call a sort of beta amino ketone or something like that. Okay? And from a mechanistic standpoint, this should be fairly straightforward to you guys. Because formally you look and you see what's happening here, right? And that's like an aldol disconnection, right? It's an aldol disconnection, but it's an aldol disconnection where instead of having an alcohol, it's an amine, right? And so in this case, instead of an aldol reaction, it's a monic reaction. So it's going to be an enol reacting with an aminium to generate amines, okay? And so again, the idea here is that aldehydes are more reactive, right? So aldehydes will condense faster than ketones, as we've sort of seen in the past. And the first step in this process is the ammonium is going to condense, right? So you can think about it as proton transfer followed by condensation. So right? And then we've all done this mechanism a number of times, and so we should be able to get to the aminium. Okay? And so now that we're at the aminium, right, all that's going to happen is your aldol or your enol is going to react in. And so we have the ketone here. As we've seen in the past, the ketone will exist as this mixture of ketone-enol polymer. Under acidic conditions, you're not going to generate an enolate. But what you will have is a small percentage of the enol form. That's going to react. And following it, deprotonation, you're going to get this oxygen, okay? So with that, I'm going to give you guys one mechanism, and I'm going to do an experiment today. This will be on your exam. I'm not going to show you the answer to it. I just saw it pop up. This is my experiment of telling you guys something that's going to be on the exam and seeing how many people actually get it. Don't expect this that much, okay? Okay, so first, ammonium cyanide. I'm not going to go through the mechanism. This is for you guys to figure out on your own. Come to the exam prepared to answer it. Ammonium and cyanide, first step. Second step, water and acid. And the product that you get is that. What kind of molecule is that? That's an amino acid. Okay? I'll even, this is a name reaction as well, called the Strecker amino acid reaction. very valuable reaction. Again, obviously amino acids are very valuable. This is a way that people will use to actually make unnatural amino acids, which can then have a lot of value in terms of unnatural peptides and so forth, and studying different biological processes in that standpoint. So, and it encompasses sort of this type of chemistry and a lot of the chemistry that we've learned. So have fun with it, and it'll be on the exam. 1 point.